Close equivalent to
hold on, can you spell that for me? Can you spell that for me?
Like when you get the minor cards, like or like you're having a playful wrestling match between you and your brother. It's like you strap like you know what I'm talking about?
My brother, I'm in trouble with him.
There you go. So you know the feeling when you know like what.
Yeah, I know how to do it. Brother.
Let's go.
I thumped my knee into this movie.
Dude, someone broke one of the chairs back there. The chair bent open and cracked. And then when I started to stand up, it pinched me. And then I'm like, it felt like I got bit. It was just a chair.
You should throw the chairs. I'm sorry.
Sorry, it wasn't fair. Mine's prepared to see.
I was like, yeah, let me take like my protector scratch. It's like if you could like type in some little SCP, it'd be nice. I could make
I'm like far front left.
the hardest part would be actually getting that level to show it on screen.
Second row. Okay, yeah, super.
You got a thing on the back of calculator? Let's go. That's sick. Hold up. Let me show you what's on mine. Magic.
I think I'm accepting DIS. So like, that's why, like, if you look at the very, very last part, it says,
Medium microphone batteries.
I think what it requires is you have it unmuted. Oh yeah.
But the thing is, like, she didn't know where she wanted to write, so where she Apparently, there's some glare on the video quality. Has anybody seen that?
Well, I was just seeing if it would
How many
maybe.
looked at the videos? Did you have any problems seeing it or not? All right, because I think the light will help, but tell you what, we'll try it with the light. If there's a problem next time, no light.
Because I thought like the whiteboard had glare on it.
It's the glare from these lights.
No, I thought it was from
Yeah,
those.
well,
Definitely
like
from
this
those.
light, it's easier to see with the light. So
Okay, just
try
keep it on, yeah.
Okay, so today, now on that quiz, there were 2 solutions that were acceptable. The grades are pretty good. One is if you had a length, remember what I told you is anything less than 1/10 of a wavelength is actually going to be a problem. Then it doesn't look like a transmission line. How many remember that? One of the solutions was a length of 0.095 lambda. That's at the cusp of not working right. So if you did that, I still give you full credit, you did it right. The other one is basically going and to the opposite point, and I forgot the exact length, but both solutions are up there. Did you all see the solutions? You didn't see the solutions? They're up.
They're up there.
They're up, promise you, on OneNote. And just take a good look. If you have questions, I'll go over it with you. But you got credit for either one. One of the biggest problems I saw was a lot of people didn't go and do it the admittance. They did the impedance. It is a series you do impedance. If it's a shunt, you got to go to the admittance domain, just to make sure everybody knows it. Now, please take a good look at that. If you have questions on Monday, we'll go over it. Today, I wanted to focus on transient analysis. Now, the solutions are there, so just take a look at that. Transient analysis is something that you have to have a fairly good understanding of, but it's also intuitive. So here's what I mean by that. Now, just please pay attention here. This is not one of these things, you can get it on your own, but it's a lot easier to pay attention. I'll show you the tricks. Normally, we start with a battery here. We're going to have plus or minus some, I'll just call it V naught. All right, that's going to be or I'll call it VS. VS. Just some V of S. Now, doesn't matter what it is. Then, I'm going to have a resistor here, and we'll call that RS. And then we're going to have a switch. So it's going to be a switch like this that closes at t equals 0. It doesn't have to close at t equals 0, but it's a logical point to make it close at t equals 0. Then this connects to a transmission line right here. So the transmission line itself has a characteristic impedance Z naught. It also has a velocity V phase. Usually it's C, but it doesn't have to be. Do y'all follow me? Does it work now?
They're out of batteries.
Don't worry about it. I'll talk loud, all right? And I'm going to try to make this clear. So here we got a switch, and you're familiar with Dave Irwin's circuit problems where you get a switch like that. Let's try to make this even bigger so you can see in the back. Characteristic impedance Z naught, and the phase velocity is C, but it doesn't have to be C. C is 3 times 10 to the 8 meters per second. It can be fractions of C. Y'all with me in this class? Doesn't have to be. The thing is going to have out to here a load, and I'm just going to put a resistive load here, so I'll call it R load. And at this point, I tell you what happens. So if I have this, once that switch closes, it starts a voltage waveform plus to minus here, or an electric field here. It'll propagate at the velocity on the line until it hits this. Do y'all follow me? The load? And then some of it's reflected. This should make sense to you. It comes back here, it hits, there's an impedance discontinuity here, then some of it hits and it reflects back. How many understand at least the thought involved? Right? It's just a reflection problem, a ricochet problem, like an echo. So the way we do this, first we need some information about it. First thing, the order isn't important, but we need the reflection coefficient at the load. Now, what is the reflection coefficient at the load? Always the impedance you're going into, right? That would be RL. Minus the impedance you're coming from, which is Z naught, over RL plus Z naught. Now, this could be negative or positive. You all with me on this? And if it was a complex load, see, complex loads don't make sense here because we're not yet at constant frequency. This is a transient problem. For us to do a complex load, this is later in the course, I'd have to write a differential equation and solve it. So just bear with me on this. I'm not going to write now, I'm trying to make it simple. So that's the reflection coefficient here. Now the reflection coefficient here after the switch, this is tau source, after the switch closes. Remember Thevenin's equivalent, when you did a Thevenin equivalent circuit, how many remember that? All right, one of the things you did, this is an ideal source, if you wanted the Thevenin equivalent resistance, you shorted the voltage source and looked at the net resistance or impedance across an element. Do y'all remember doing that? So here it's RS. Now when this wave is coming this way, so there's a reflection coefficient here, this is going to be RS minus Z naught over RS plus Z naught. Everybody follow me on the thoughts? Yeah.
Is that a gamma S or is that a RS or what's that symbol?
Right here?
No, on the left.
That's gamma. It's the reflection coefficient. I'm trying to show you the symbol is the Greek capital T. That's all it is. It's the symbol, standard symbol for reflection coefficient. The sub S is source, sub L is load. Everybody with me? Okay. Now, the way we do this problem, we're going to say as this switch closes, at the instant it closes, it will develop a voltage right here that we call V prime. This is the instant the switch closes. So what would V prime be? So this is at T equals 0. The actual V prime, and here's what it looks like. When that switch just closes, this looks like you have a source right here of Vs, a source resistance of Rs, and then you have an actual impedance here of Z naught. Now it doesn't know, just think about it. As soon as this closes, it doesn't know how long the line is, and I should put that in here now. Call this line length L. It doesn't know anything. The instant it closes, the only thing it sees or can actually determine is the characteristic impedance right there at a transit. Y'all with me? So when we get the voltage right here, this is at T equals 0. This is at T equals 0. No, I didn't. Can you go back and grab them from her? Where's my man? There it is. Oh, thank you. Great. And you want to do me another big favor? Can you put them in there? Thank you. Don't worry, I'm not going to go that fast. All right, now, does it make sense? We can find V prime at T equals 0 just by taking Vs here and then times Z naught over Z naught plus Rs. It's simple voltage division. Do y'all agree with that? All right, now that waveform at that point, just think of this. You got this wave, there's a plus to minus V prime here, and it's propagating at the velocity on the line that's allowed to propagate. I'm going to show you the trick on this. Now it hits the load, and then some of that reflects back. How much? Well, it'll be the amount that hits times the reflection coefficient. You all with me? And that reflects back. That reflection coefficient, thank you very much, sir. That reflection coefficient will always be equal to or less than 1 in magnitude. All right, always. As a matter of fact, the only time it's 1 is testing. If I need to lower this stuff, you know. Test. Can you hear me? Mm-hmm. All right, I don't want it too loud, but you can hear me good. All right, so now you take a look at this. All right, we have V prime there, and here's the trick in this stuff. It's called a bounce diagram. This is in the book. Does anybody have a book here? Can you see where that bounce diagram is? You're looking at it right there, at the bottom of your page. What page is that?
89.
Page 89. This is called a bounce diagram. Here's what you do. This is going to be the source point. And this is the load. Now, it really doesn't matter about if you want to call this minus L or 0 and this either 0 or L. It really doesn't matter. But you know here's how this works. On this axis, we plot time. Right? So time, this would be 0 right here. Now, on this axis, what we're going to do is show you where the location is of the waveform that's bouncing. And you'll see this in a second. So now the next thing I need is, I need the time it takes. I think he calls it T-sub-L. The time it takes for the waveform to go from one end to the other end. You all follow me, class? Well, if you know the distance, L, if you divide that by the velocity, you get the time. Everybody follow me on that? So if you say this is just going to be L divided by V phase. V phase usually is C, maybe 2/3 C. Nothing crazy. You all with me on this? It's not going to be some odd, really odd thing. So now, you come down and you make marks. And this is where that engineering paper is nice. You know that light green kind of crosshatch paper? This is really nice for this, or any kind of graph paper. What you do is going to say this is TL, this is 2TL, this is 3TL, and so forth, 4TL. So if TL was 1, say, or 5 nanoseconds, that'd be 5 nanoseconds, 10, 15, 20 nanoseconds. You all with me? Some of you already figured this out. So what happens is this thing is going to go, you draw a line like this here, and this is going to be just V prime coming down here. Remember, you energize it, it's just showing you the location of the wavefront, and this would be spatially, you can call it Z here if you want. Spatially and temporally where that bounce is, if you will. Can you all follow me, class? Now when it hits here, now they're going to get one that goes back. And let me try to draw this. I'm trying to draw this in a way that's going to be a little more, I'm trying to be as accurate as I can about this. This is not going to be drawn to scale, but it's close, hopefully. So this one comes down, it hits here, then it comes back, hits here. Just do this with me as best you can. And here, it's showing the book. Now, next thing I'm going to say is this. This waveform here, just as the switch closes, that's a T equals 0, this sends a wave that has a value of V prime in this direction, okay? Let me just stop for a second. So if I wanted to know the value of voltage versus time at any point on this transmission line, suppose I wanted the value of voltage right here. I mean, this is going to be the distance away. You with me? I go straight down. There's no voltage at all. Then all of a sudden I hit V prime. So at that time, I know the voltage would go from 0 to V prime at that point. You all with me? Then it keeps going, it hits. Right? So this is V prime. Now what's coming back is going to be V prime times the reflection coefficient at the load. Make sense to everybody? You with me? It hits. The reflection coefficient times the incident voltage is the reflected voltage. All right? That keeps going here, this way, and then it hits here. When it hits here, it takes that voltage right there and it multiplies it by the reflection coefficient of the source. So that means this voltage right here is going to be gamma source, gamma L, times V prime. Getting the feel of it? Right? Think about it. That voltage that hit here was V prime gamma L, right? Multiplied by the reflection coefficient, which is gamma S at the source. Can everybody follow me on this? You good with that? Can you see it back there? Now that's the voltage going here. What is this value going to be? Remember, this is gamma L, and this is gamma S as the reflection coefficient. What do? Just take that and multiply by gamma L, right? You'll notice you get gamma L squared here. So this is going to be gamma L squared, gamma S times V prime. And the process goes on and on and on. You can just have an infinite number of these. Now this thing's going to asymptotically approach a steady state value. I'm going to do the plots, but I want to just show you something. I want you to think about this. This is a transmission line that's lossless. It really is a couple pieces of metal separated by dielectric, right? As time goes to infinity, what do you think the voltage here will be? I want you to just think about it rationally. Well, effectively, you can remove that transmission line, because as time goes to infinity, all this bouncing is going to die down to nothing. It's going to just go down to a constant. You all with me? And the value here, as time goes to infinity, will just be Vs times RL, as if the transmission line isn't there, Vs times RL over RL plus RS. It's voltage division. All right? How many see this right here? Are you with me? Can you guys see it? All right. Now, I'll show you the next thing, because sometimes when you're doing these, you get a little confused. You don't know what you don't know, but there's something that really you don't know, and you're doing it. So I'm going to try to make it clear. Let's suppose we want the voltage right at the center, at L over 2 down the line versus time. Can you all follow me? I'm trying to graph that right down the middle. And I'm going to remove this. I'm going to show you the voltage. I think I like this one better. By the way, is anybody going out to California for the game? I'm going to say good luck. Long trip. I used to have people in the marching band in my courses a lot of times. They always come back exhausted. Okay, back to this thing. Here's the deal. We want the voltage versus time right at the center of the line. Can you all follow the actual trajectory here, right? And let's, for kicks, put a value on here. I'm going to assume the length of time it takes to go down the line is just, say, 2 nanoseconds. So just assume it takes 2 nanoseconds to go from one end to the other. So now we're going to graph the voltage at the center of the line versus time, right? And it looks like this. Here's time. Now, this is going to be the voltage on the line. And it's V at, really at L over 2, right in the center of the line. You all with me? Can you all follow me on this? Now, instantly, if you look, the way you do is come here. There is no voltage that's propagated down. So it's 0, right? It's 0 until I hit this point, and then it goes to V prime. So what you do is come down here at TL over 2, which is going to be 1 nanosecond right here. Now it goes up. It comes to V prime. Can you follow me on this? Go ahead. If you got a question, ask it.
Is that L over 2 in the middle of the line right there?
Yeah, I'm trying to say this is dead center, right?
Yeah.
Let me try to erase that. It's right in the center. This is the easiest one to see. So I'm saying I'm right in the center of the line, and I want to see, I want to plot the voltage that would occur between the upper and lower conductor. So this is an L over 2 here. It's going to stay that value for how long, class? Call this TL. Call this 3/2 TL. And let's keep going. Call this 2 TL. 5/2. 5/2 TL. 5/2 TL. And so forth. Now let's just think about it. With me? I saw, came through, got it's an instantaneous change, theoretically. It's not actually that, but it's close. Goes from 0 to V prime. Stays there until I hit this, right? Now you add that to the value. You all hear me? Just add it to it. So now we add V prime plus gamma L on that. So right here, and where does that occur, by the way? How long does it take to get to this point? Well, how long did it take to get from here to here? TL, right? From here to here is TL plus TL over 2, or 3/2 TL. Do you all see that, class? Can you all see it? All right, it's just ricocheting. So now at 3/2 TL that I'm drawing right here, now, and it depends what the value of TL is, now I'm going to say it's positive. Now it goes up, and the total value here is going to be equal to V prime plus V prime TL, or it's going to be 1 plus TL times V prime. Can you all follow me? And the only thing I'm doing is adding the value of the reflected wave. Everybody see this, class? How many do? Trying to follow your eyes and see if you... Okay. So now what happens? How long is it going to be at that value, class? It's going to be exact, right? I've chosen things right in the middle. So the next transition is going to be where? 5 halves, right? And now what happens? Just look. Now I'm going to have V prime plus V prime TL plus V prime TS TL. You all follow me? They're all added together. So this, and I don't know, I'm going to have it go down. Now this value is going to be simply, that's going to be 1 plus TL plus TL times, gamma L times gamma S right here, and it's going to be times V prime. How many see the progression of this? Go ahead, you had a question.
Yeah, why is it going back out? Shouldn't, since you're adding another, no?
Now, here's the deal. His question is legit. Suppose gamma L is positive. It would mean that the source or the load resistance is greater than Z naught. You all agree with that? But this one will be negative. All right? So if it's negative, then this will cause the net voltage to go down. Do y'all follow me? All right, you with me on that? All right, now keep going on this. What happens? Well, asymptotically, the thing's going to ricochet, and there'll be less and less change, and eventually the value that will be in the center here of the line will be the value of the load at the load, and it will go to simply Vs times, and then it's going to be RL over RL plus RS. That's what we'll asymptotically approach. Can you all follow me? How many at least have a fair idea what's going on? The best way to do this is do a couple of problems and allow yourself to try to reason through them. Don't let me do them, just tell me what to do by yourself. So in the book, he's got a lot of problems. And there are some subtleties. And I'll get to those. Yeah.
Quick question, I know you just explained it, but I see in the book that it does turn negative, but can you just explain one more time to me why it's negative?
Let's just assume this for a second. Let's say I didn't have it drawn here. Suppose the source resistance right here is 50 ohms, all right? Let's assume the load Z0 is 100 ohms, and I'm just picking numbers, all right? Now let's assume RL is going to be 150, all right? So I got a load impedance, I got a characteristic impedance of the line, and I got a source resistance, right? So let's figure out what the reflection coefficients are. For gamma L, that's at the load, it's the impedance you're going into, which would be 150 minus the impedance you came from, which is 100, over 100 plus 150 or 250, right? That's going to be positive. Do you all see that, class? It's a positive value. What is it? That's, what, 50 over 250, so it's one, is that right, 1/5? Yeah, 1/5, right? Agreed? Now, what about the source impedance? Well, it's the impedance I'm going into is 50. Do you see it? So it's 50 minus, and then you can say Z0, which is 100, over the sum is 150, right? So that means gamma source is equal to what? Minus 130, correct? Yeah. That's why it's negative. So when you take a look at this voltage right here, you'd have 1 plus a positive value, and then a positive times a negative is a negative, then minus that it would be less. That's the only, yes sir?
So if you did graph this out through like a ton of time steps, it would approach the like exponential curve?
No, not exponential. It asymptotically approaches the value. It'll just ricochet, and the actual delta changes will be less and less and less. And then it'll asymptotically approach the value of the source voltage times the load resistance over the sum of the load resistance plus the source resistance. It's simple voltage division, that's all it is. as time goes to infinity. Because as time goes to infinity, that transmission line looks like a couple of wires connected. It doesn't look like a transmission. Everybody with me? I hope that answered your question. Now, let's go to do the problem.
So I'm assuming like we're gonna do problems of turning flipping the switch back off and turning it into.
That comes later. You're ahead of me, but he's saying, well, what if the switch goes on and then goes off? That's a pulse.
Yeah.
I will do that, but first let's do these so everybody gets a little comfortable with the math. And let me erase this. So this is section 2.8 on page 111 in my book. And we're going to go ahead and do problem 2.43 in a second. I want to erase all this stuff first. You're going to see that this stuff is not hard as long as you understand the basic theory. Where it gets really difficult is if you're confused about one small aspect of it, then usually the whole thing you'll mess up. Okay, can somebody read me problem 2.43? 2.43. I know the velocity on the line is what? Phase velocity is 2/3 c, I think, isn't it? For that one? Say it. Anybody want to read it to me? I got a book.
Consider figure 2.35 with the following values. Vs equals 10 volts. R sub S.
Oh, never mind. This is 10 volts of source voltage? 10 volts?
Yes, sir.
Go ahead.
R sub S 30 ohms. R sub O equals 50 ohms.
RS equals 30.
U sub C.
Oh, hold on. Let me just switch. And what is Z naught, the characteristic? Anybody?
It's
He'll say the impedance of the line transmission.
50 ohms.
Is it 50? Okay, 50 ohms. All right, now hold on. Down here, what's the load?
150 ohms.
All right, our load is 150. Very similar to something. That's 50, right? And that's 30, correct? What's the length?
10 centimeters.
L equals 10 centimeters. And what do they want? Is that right? The velocity is 2/3 c, 0.666 c? Okay, got it.
The voltage at the source end, voltage at the middle, and the voltage at the lowest end of the line.
All right, what we're going to do first is get the voltage at the middle. We just did this. All right, so to do that, and the order is unimportant, but I've got to find the length of time it takes for the wave to get from one end to the other. And I call it, and he does in his book, just TL. So that's equal to the length over the phase velocity. The length of the line is 10 centimeters, so that's really 0.1 meters. The phase velocity is 2/3 of c. So that's 0.1. C is 3 times 10 to the 8th, so it's over 2 times 10 to the 8th. And that comes down to what? That's going to be 10 to the 8th, 10 to the 9, 10 to the minus 9, so it's going to be 1/2 times 10 to the minus 9 seconds. Isn't it, class? Tell me if I messed that up, right? 1 over 10 to the 8th is 10 to the minus 8.1 is 10 to the minus 9. 1/2 times that is going to be 1/2 in that a second. Do y'all agree? Give me a show of hands. Y'all with me on this? That's the first thing. Next, we need the reflection coefficient here, right? So what is the reflection coefficient for load going to be, class? Think about it. Impedance you're going into is 150. Follow me? It's 150, right? Over or minus the impedance you came from, which is 50, over the sum, which is 200, right? So that's going to be what? 1/2, isn't it, class? Everybody follow me on this? Okay, what about the reflection coefficient here? Now, this shuts at t equals 0, I think, I hope. What's the reflection coefficient at the source? Class? Well, it's always the impedance you're going into, which is 30, right? Minus the impedance you came from, which is, because that's the way it's bouncing this way. Follow me? It's going down and coming back. Minus 50 over the sum of the two, or 80. What's that going to be? That's minus 20 over 80, or minus 140. You agree with that? The other solutions, I know they're posted. If anybody can get to them, I'd appreciate it, but I just want to confirm what I'm doing. Y'all with me? All right, now we got two of the things we need. We also need this V prime, right? That's the voltage that would occur just as that switch closes. The way we get it, this is at t equals 0, the only thing we do is take 10 volts, right? Then we put RS there, which is 30, which is nice. And then we put the impedance of the transmission line, which is 50. I'm going to call it Z naught. And we need this voltage right here. We need V prime. So what's V prime going to be? Just by looking. It's 10 times what? 50 over 50 plus 30. So it's really what? So it's 10 times 50 over 80, right? So what is that?
6.25.
All right, 6.25 volts. And that's V prime. Can everybody follow me on the reason I'm doing it? How many can? In the back? You guys got it? All right. Now we do the bounce diagram. I'm going to assume you got that written down or understand. So now the bounce. Now we're going to get all the things we need from this bounce diagram. So, and this is always the same as far as the look. It's going to have things like this, and this is going to be time on this axis, and this is distance. Doesn't matter if you call this point 0, 0 or not. And then after that, you go ahead and you start what, like this. Bang, 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 bang. Each one of these is located. Each time it goes down, this is TL. This right here is TL, not drawn very well, 2TL. This right here would be 3TL, and so forth. I'm just going to take it out to there. But you all follow me on this? And you could write this down. You could say this is what, half a nanosecond. So right here would be 1/2 nanosecond. This would be 1 nanosecond. This would be 1.5 nanoseconds, and so forth. We'll just go to here. I normally, when I do these things, I recommend you put the value of the reflection coefficient here. At the low, the reflection coefficient was 1/2. And down here, the reflection coefficient of the source was minus 140. Can y'all follow me? Take a good hard look at this. It's not hard to see, but you got to be attention. Now, I'm going to come over here, and I'm going to graph the bounce diagram for the voltage at the center. There's a few subtleties coming up. This one we should get. I think we're going to have no problem getting. So, if we do this, this is going to be at voltage at really L over 2, or center of line. So if we take a look at that versus time, now think about it. What we're going to do is come over here. We want the voltage at the center. We come right at L over 2 here and just draw a line straight down. Can you all follow me on that?
Just for begins to you, what did you do right next to VL over 2? What does that say?
What did that want?
What does that say next to
It's
VL?
center here.
Okay.
My handwriting is horrible. Sorry.
No, it's okay.
Got a lot of pain in my knee right now, so wasting a little. You all with me, class? All right. Let's do this. Here's where I start. right? That's the point. Time equals 0. Can you all see this? Remember, this is time down. I keep going, nothing happens until I'm at this point. What's that time, class? TL over 2. Isn't it, class? It takes TL to get down the line, it would take TL over 2 to get half of that. Do you agree with that? Or not? I'm looking at you. You got it or not?
Yeah, you reset that?
Yeah, if this thing is total length
Oh,
L,
you go, okay, I'm good.
Uh,
But you're talking down.
and I mean, to get to this point, it would take that long. I'm sorry if I did. All right, so I'm going to take TL over 2 here and just put it down. Now, what is TL over 2? Well, it'd be 1/2 nanosecond, right? Divided by 2 or 1/4 nanosecond. You all follow me on this? I'm just going to leave this TL over 2. And then what happens? What does the value go to? Did we get that? Or not? I need V prime, don't I? What is V prime? No, we did 6.25. Didn't we, class? Remember us calculating? How many did? All right, 6.25. So now it goes up right here to a value of 6.25 volts. And that is nothing more than V prime. This is at the center now, right? At L over 2. Keep going. What happens? I come down and I hit, this would be TL, this would be 1/2 nanosecond. Then I have to go to 3/2 TL, right? Do you agree with that, everyone? And what happens at this point? Now I have to add something, right? I've got 6.25. I have to add the reflection coefficient 1/2 times 6.25. How many understand that? So this comes down to be a value right here. You can give that to me. Right here, it's going to go up, and it's going to be really 6.25 times 1 plus 1/2 reflection. Or what is that? 3/2 times 6.25. What's the value here, guys? It's not up. Yeah, trust your calculator, especially if you're tired. Can you give it to me? 9.375. All right, so that's what this is. 9.375 volts, right? Now, how long is it going to stay there? I think you guys got this. Well, from each one of these, I didn't put this down here, but this is V prime. This is gamma L V prime. This right here, this one is going to be gamma L gamma S V prime. And this one this way is going to be gamma L squared gamma S V prime, and so forth. You all follow? This is the progression. So this way it hits. We're tracking the actual propagating wavefront, and we're adding it at each point necessary. So over here, what happens? That's 3. So this would be what? That would be 1/4 nanosecond, correct? This would be 1/2 nanosecond if we wanted to. This is going to be 3/2, really. Not so. That's going to be 3/4 nanosecond, and so forth. But I'm not worried that much about the times because everything scales. Once you have TL, you just multiply it by the fraction. It keeps that up until what? Well, every time the thing goes through the middle and hits, it comes back, it has to go a full time constant. All right? So then I come down here, so this is 5/2 TL. And what does it go to? 5. This is the value it had. Well, you can do it 2 ways. You can take that value, right? And just add what to it? Gamma L gamma S V prime. You all see that? Or you can write it all down if you want. And you can just say this value is going to be down a little. This value is going to be V prime, or 6.25 times 1 plus gamma L plus gamma L gamma S. You're going to see this number is smaller than gamma L in magnitude, but it's negative. So what do you get for this? This value is, class, anybody? 1 plus 1/2 minus, what is that? Minus 1/8. Anybody? Anybody? I appreciate you doing it for me. This is minus 1/8, right? This is 4/8. Right, so this is going to be 3/8 plus 1 times 6.25. Or to 11/8.
8.594.
Say it.
8.594.
All right, so this is 8.594 volts. And how long is it going to stay there? Say it. Exactly one time constant, right? So here it's going to do a transition at 7 amps. And this is not drawn very well, PL. And now what's the value going to be? Just let's finish it up. Now we went what? Went here, here, here. Finally, what are we going to do? Gamma L squared, right? 1/2 squared is 1/4 times gamma S, which is going to be what? Minus 1/16. You agree? And you're going to multiply by V prime. So what is this value going to be? I think it comes down again, I think, right? So this is going to be equal to 6.25 times 1 plus gamma L plus gamma L gamma S, and finally plus gamma L squared gamma S. And you can tell me what that value is, but I'm going to make a point here in a second. It's sloppy, I'm sorry, but I hope you follow the trend. Anybody give me that value? It's going to be close to, if that's 8.94, it's going to be close to that. 594. Anybody? I appreciate you. What'd you get?
8.20.
8.20. I believe that. 8.20 volts. What are you noticing happening? Just take a look. This thing starts at 6.25. Then it bounces up to 9.375. Then it bounces down to 8.94. Then it goes down to 8.2. What do you think it's going to end up at as these bounces become less and less? I mean, in terms of, what is it going to go? The net change will be 0, but the actual value it asymptotically approaches is what? It would be what? Think about the problem. Forget the transmission line. Just get rid of the transmission line. If I have a voltage here, was it 10 volts, class? And what was the source resistance? 30? Was it? And what was the actual load?
150.
Not the characteristic. It wasn't load. 100, wasn't it?
150.
Was it 150? Okay. If this is 150, this is what this voltage right here, and I'll call it V load as t goes to infinity. That's it. So V load as time goes to infinity will be equal to 10 times 150. Just tell me what this is. Over 180. So I don't know what that is, but that's what it's going to approach. Did it get done?
8.33.
You see how close we are already? A few more bounces, you won't be able to tell the difference by your eye. Generally speaking, with transmission line problems like this, after about 5 or 6 bounces, pretty much steady state. That's the thing you just keep in mind, and you'll see why. Now that was in the middle. Everybody agree with that? Take a moment, make sure you're convinced. Everybody? Now we're going to do it at the end. What? Am I overtime?
You got 3 minutes left.
All right, we'll do it at the end. That stays up. This comes down. I think you guys get it. I really try to make this simple. I'm not going to give you any differential equations right now for the loads and all that. Just try to make it as simple as possible, because this is 99% of everything you need to know right here with transients, in my opinion. All right. Now let's do it at the load. So now we're at the load. We want V of load. That is going to be really at L. Now, let's just do this together. This is the voltage on this axis. This is time. What does it start out at the load as that switch closes, class? 0, right? There's no voltage. Until what?
The switch is closed.
TL, right? I mean, TL closes at 0, so it takes TL, or half a nanosecond to get there. So this is going to be TL. Now, At that point, this is important. Here's where people make mistakes. At that point, we have a superposition of a wave coming in and reflected. Can you all see that? At that point, you have to add V prime plus gamma L V prime to get the voltage at the load. Because simultaneously, as one's hitting, another's reflected, it's a superposition of the two. So this voltage here, that somebody can give me, is going to be V prime or 6.25 times 1 plus gamma L, and that's going to be about 9 something, right? 9, I forgot, 25, is that it? Say it again? I appreciate you calculating. All right, 9.375 volts right here. All right, how long is it going to be there? Class? Think about it. Waveform came down, TL. Came down, 2 TL. Came down, 3 TL. Right? It has to go down and back. So then you come out, if that's TL, here's 2 TL, here's 3 TL. Right? Now what's going to happen, class? Just think about this carefully. Now, watch me. All right? So this comes down, this is coming, right? The incoming waveform here has a value of gamma L times gamma SV prime, right? The reflected waveform has this, gamma L squared gamma SV prime, right? You have to add both of those to the original value. Y'all with me? Because they simultaneously intersect right there. One's coming in, the other's reflected out. So now over here, it's going to be what? I'll write it down. And I think this is negative, but I'm not sure. So this is going to be equal to 6.25. Then it's going to be 1 plus gamma L. That's what's there. Then it's going to be gamma L gamma S. And plus, finally, gamma L squared gamma S. And if you can give me that number, it'd be great. It's not going to be a huge difference, I don't believe. It's actually going to be negative. What's it?
8.20.
No, it sounds about right. 8.203 volts, okay? Now you all see how we're just tracing the bounce diagram, but we have to be careful that at points, at the end points, you superimpose the incoming and reflected signal at the time that they occur, all right? Now go ahead. Somebody have a question? All right. Last thing I want to say is this. Well, we're at the end over here. What do you think happens? Well, when we started right there at t equals 0, it's just V prime. You see that? Keep going down, but at this point, 2 gamma L, or 2 tau L. Now you have to add this and this simultaneously. You all see that, class? They occur simultaneously. That's it. I kept you on. Hey, could I get the extra quizzes if there's any extra? And your grade should be on OneNote. Canvas.
Yeah.